I think we were on this slide. Okay. So first, just want to wait. Okay. So first, I would like to remind you. Okay. I think like the project 3 and the final project has been up like for a long time, but okay. So I also have the TA uploaded the sample final as well as the handout for the next 2 chapters.
哦，有的。
红笑，感觉没电了。
没电了吗？可是它这里。
有绿色，它过一下又变红，这应该是没电。OK， 谢谢。确认一下 ，OK。好。Yeah. So I mean, the last word, I mean, should be obvious to you by now, okay? But what is mean average then? Because these two words, I mean, means the same thing, right? Mean, average. I mean, they are both like average, right? But they actually mean different things, okay? So this is like when we visualize the precision recall curve, okay, you can see something like okay, most of the time, mean precision curve goes down like this. Okay, so the higher the recall, the lower the precision. Okay, and the higher the precision, the lower the recall. Okay, most of the time. But sometimes you do see this type of glitch. You can see these glitches. Okay, so in this type of situation, okay, let me give you an example. Okay, so okay, suppose the classifier has 90% precision at 10% recall, but 96% precision at 20% recall. Okay, this could happen sometimes. Okay, most of the time, as I say, like when the recall, increases, the precision should be lower. Okay, but sometimes because of a little bit of glitch, okay, yeah, this could happen. So when I say trade-off between precision and recall, but in case like this, there's no trade-off, right? Basically, okay, there's no brainer that you should, okay, anyone with with common sense should pick up. Between these two, everyone with common sense should pick like, okay, we want 96 precision with 20% recall because, both precision and recall are better, right? Okay, so that's the issue. Okay, so so instead of looking at the precision at the 10% recall, what we should look at should be the maximum precision that the classifier can offer with at least 10% recall. Okay, so under the condition with at least 10% recall, how good, what is the maximum precision you can have? So, for example, so like in a case like this, okay, at least 10%. So, I mean, in the 10% and the 20% are both included, right? So, 10% is 90% recall. 10% recall is 90% precision. So 20% recall is 96% precision. So the maximum precision should be 96%. Okay, should be 96%. So this is something we should consider actually. I mean, when we use the really put this model into usage anyway. So what we are going to do is like this, okay? So so we consider the maximal precision you can get with at least 0% recall, with at least 10% recall, with at least 20% recall, and so on, up to 100% recall. So you are going to get 11 maximum precisions, right? Based on different minimum recalls. So we are actually going to, average those precisions, and we'll call this matrix as the average precision. Okay, average precision. Okay, the reason to consider this is just because, as I said, even though precision recall are trade-off, but sometimes when recall increases, precision not necessarily always decrease. Okay, especially at the border. At the border, when the precision, when the recall is close to 0%, or when the precision is close to 0%, something strange could happen to make like a sort of like a glitch, and those glitch can affect this type of consideration. So we use this average precision, okay, to capture all this tiny impact, okay, in the precision recall curve. Okay, so now you understand what average precision is, right? Okay, we are not done yet, because obviously there's still one word missing, right? So so remember, okay, this precision recall, okay, just like the AUC ROC curve, okay, because we consider binary classification, right? But most of the time, as I just mentioned, okay, we are talking about multi-class classification. So most of the time, we are dealing with more than 2 classes, right? So, for example, the example I just mentioned, if you have 5 classes, you are going to end up with 5 different AUC, ROC, as well as precision recall, right? So, okay, so for each of these 5 classes, okay, when you consider them separately as like binary classifications, then, okay, each one will give you an average precision, this AP metric. Okay, and then, okay, for those 5 classes, you have 5 AP score, and then you average those 5 AP score. That's where we get this mean average precision. Okay? So this is obviously work for the case when you have like more than 2 classes. But in object detection, for example, like a YOLO, like a COCO data set, we have tons of classes, okay, at least 20 to even like 1,000 classes. So we have to consider something like this anyway. So now you understand mean average precision, MAP, okay? But actually, the thing is even more complicated than that, okay? In an object detection system, okay, there's one additional consideration, okay? What if the system detected the correct class, but at the wrong location? Do you consider that as correct object detection? Probably not, right? Probably not. Okay, so how do we consider the location of the detection is correct or not? Remember, we talk about the IOU, right? IOU metric, right? Basically, IOU metric is used to capture to measure how accurate your bounding box is, compared to the ground truth, right? So that's like the metrics you can use to measure the the predicted location is correct or not. Okay, but you know, the previous, the MAP stuff, okay, the metric, okay, only measure the classification performance, but it doesn't measure the, you know, the localization, okay, like the correctness of the bounding box. So as I said, like if the system, okay, detect the correct hash, but at wrong location, we probably shouldn't consider that as the accurate object detection anyway, right? So what happens is like, okay, we can define the an IOU threshold. For example, we can consider prediction is correct only if IOU is greater than, for example, like 0.5. Okay, and the predicted class is correct. So we only consider that. Okay, so the MAP under this consideration is called MAP at 0.5. Okay, so sometimes we also say MAP at 50% or MAP AP 50. Okay, if there's no confusion. Okay, just there's many ways to write it, but basically it means the same thing. Okay, so in some competitions, for example, like Pascal VOC challenge, okay, this is another object detection competition. Okay, so this is what it is done. Okay, so they only consider this, you know, the MAP under the consideration that IOU is greater than or equal to 0.5. Okay, but in other competition, such as like the COCO competition, the MAP is computed for different IOU thresholds. Okay, so we consider IOU threshold to be 0.5, we get a MAP, and we consider IOU threshold to be 0.55, we have another MAP, and the 0.60, another MAP, and so on, up to 0.95, and we have MAP. And then we will add all this MAP and do another average. So it is represented as AP at 0.50 to 0.95, or AP at 0.50. Okay, I mean this 0.05 just means like this is like the steps, okay, between like a different threshold and 0.95. So this is a mean average. Yeah. So just want you guys to understand, okay, how we use this MAP matrix in like object detection. Okay, I mean completely. Okay, because when you read the papers, okay, you will see this MAP come up like quite frequently. Okay, actually, but they probably don't spend much, time to explain what is MAP or like MAP at 50. Okay, what does that mean? Okay, so you need to understand, the context of this matrix in order to appreciate like those performance comparison. Okay, so then we talked about semantic segmentation previously already. Okay, so each pixel is classified according to class of the object it belongs to. Okay, so I think I already show you this picture anyway. Okay, so you guys get an idea what it is. Okay, what the semantic segmentation is. One thing I'd like to mention a little bit more is like in the semantic segmentation. Okay, if a pixel belong to like the same type of object but a different object. For example, you see there are several bicycles, right? There are several bicycles here. So you can see the pixel here and the pixel here, obviously, is for different bicycles, right? But no, under the semantic segmentation, they all fall, into this big block, okay, big blob, okay, because these bicycles, they do not, really like separate like each bicycle, okay. So this is the semantic segmentation, okay. So so difficulty of this task is that when images go through regular CNN, okay, I mean, because remember we have like a stride, right? We have like a max pooling or average pooling, whatever pooling we use, okay. We are doing the downsampling. So downsampling, okay, obviously is going to lose some spatial resolution, okay. So at the end, when the model, okay, when the CNN model is able to tell, okay, there's for example, a person somewhere, but it may not be able to pinpoint the exact location of that person, okay. So that's the difficulty part of the semantic segmentation, and I already told you, okay. I mean, for this problem, there are many approaches to deal with that. Okay, one solution I talked about was like remember Jonathan Long? I told you like the fully convolutional network actually was proposed, okay, by Jonathan Long in his 2015 paper for semantic segmentation. Okay, so he used FCN, okay, to deal with that, pre-train CNN and then turn it into the FCN, and then apply overall stride of 32, okay, to the input image, and then okay, it has to stretch it back to 30, multiply the resolution, by 32%, times back to the original image size. So basically, what do they do? Okay, they use upsampling layer to do that. Okay, so what is upsampling? Okay. Upsampling. Okay, basically it just means like you guys know downsampling, right? I mean, it is when the when we set the stride to be greater than 1, okay, or like when we use like max pooling, obviously we also have to set the stride to a value greater than 1. Then like the height and the width of the input image will shrink, right? Okay, so those things are called downsampling. So upsampling pretty much is doing the opposite stuff. Okay, so so say you have an image, and you want to enlarge this image. Let's consider, okay, we want to enlarge this image like twice as big. I probably should say twice as big. I should say like increase the height and width. We want to double the size of the width and height of the image by 2 times, for example. If I just want you to do that, what do you do? The easiest approach is you just stretch the pixel, right? And of course, like when you stretch the pixel, there's like a pixel in between that you don't know the value, right? Okay, so you could use interpolation, bilinear interpolation. Why do I say bilinear? Because we are doing the linear interpolation on 2 dimensions, the width and the height. Okay, so we could stretch the pixels, and then for the for the the newly added pixel that with no value, we pretty much use the linear interpolation to find the value of the newly added pixels. Okay, by doing this, okay, we are normally able to increase the image size by 4 times to or even 8 times. So, and they perform reasonably well. Okay, if you want to do it like even better, even bigger than that, or if you want it to perform more realistic, but because like if you really have written a program to do this bilinear interpolation, okay, to increase the size of your image, you will find that the image will become kind of blur, okay, not very crispy, clear, okay, because we are doing interpolation anyway, right? So some of those like sharpness like was lost during the interpolation process, okay? So what do we do? Okay, instead, okay, we could use transpose convolutional layer. Okay, what is the transpose convolutional layer? Okay, in the transpose convolutional layer, we first stretch the image by inserting empty rows and columns. This part is the same as the bilinear interpolation approach. I mean, we first stretch the image. This part is the same. Okay, but then, okay, we will apply, okay, the concept of the, kernel, okay, or like filters, okay, to the stretched image, okay, to decide like what value to fill in. Okay, let me show you the picture. So say original size of the image is like the input size of the image is 2 by 3. This is the input size, and then okay, we first like stretch this image like this. So you can see the pixel, I mean, in between pixel, we insert those empty pixels, okay? Those empty pixels. I mean, in this case, the stride is set to be 2, okay, by the way. Okay, so obviously this is much bigger than the original input. But we are not just using this one, okay, as the output, okay? In the bilinear interpolation, pretty much we determine the value of this by linear interpolation, okay? Something like that. So those things are easy. But in the transpose convolutional layer, okay, on this layer, we apply the kernel size of 3 by 3. Okay, so it's like going to be, we use a kernel, we use a filter, okay, to calculate the value of this area and put it here, and and so on, okay, and then this is going to be the output. It's going to be 5 times 7 output. So you can see this output still much bigger than this one, right? Okay, so the transpose convolutional layer first stretch the input and then apply something similar to what we did in the convolutional layer, the filters. And because remember the filter, okay, each filter has the weights, right? Each filter has the weights, and those weights are learnable, right? So pretty much, I mean, the weights will decide like what is the best way to determine the value in here. Okay, I mean, obviously, like if it doesn't learn very well, okay, it probably just learn the bilinear interpolation. But if it is able to learn better, then the performance is going to be much better than the bilinear interpolation. And the result, yes, it is better than bilinear interpolation. Okay, and this is, the the transpose convolutional layer that we can use for upsampling. Okay. So okay, not only that. Okay, they also use like in like TF dot keras. Okay, you can use the conv 2D transpose to create the transpose convolutional layer. Okay, if you want. Okay, and then okay, you know, not only that, they also use the skip connections when they, you know, enlarge the figure, because if you only do the transpose convolutional layer, sometimes the information may not be enough to really like you know, get a good job done. So what we do is like okay, we can let me show you. Okay, it's like this. The concept is like this. Okay, so this is the original feature map, and after the downsampling, it was shrink to like something like this, right? Remember, this is a model that is used for the semantic segmentation, right? So the input image originally was big, right? And then we use downsampling, right? Okay, so we have a larger image at the earlier part of the model. We do have those, okay? And then, okay, say we downsample to like this. Now, when we want to do the upsampling, okay, not only we use, in here, not only we use, you know, the transpose convolutional layer, but also we incorporate the feature maps of the previous layer with the same size. We add them together, okay, and then we again use the upsampling, okay, 16 times, okay. If you don't have the information from, I mean the larger feature map from the earlier layer, you are not able to, you know, increase the size by 16 times and get a good result. Okay, I mean the transpose convolutional layer, you know, if you add, just increase by 2 times, I mean it can perform well. Okay, just like a bilinear interpolation, yeah. If you want to increase by 2 times, 4 times, it performs reasonably well. Okay, the transpose convolutional layer, 2 times, 4 times, even 8 times, it performs reasonably well. Actually, better than the bilinear interpolation. But if you want to increase to 16 times, then you need additional help. Okay, in this case, I mean, you can see we use like the earlier larger feature map to help with that. Okay, so this is like you know, how the Johnson long, okay, is able to, you know, enlarge the figure, okay, after determining like the class and the how did he upsample it to 32 times bigger, okay? It's something like that, okay? Not only transpose convolutional layer, but also he used the skip connection. So it's just okay. So GitHub repository provides TensorFlow implementation of semantic segmentation. Actually, there's even like a more advanced semantic segmentation called instance segmentation model. Okay, that is available in the TensorFlow model object. Okay, what is instance segmentation? The instance segmentation, you know, it's just like okay, here, okay, as I said, like if the pixels belong to different bicycles, okay, if you are talking about semantic segmentation, they all fall into the same blob, right? But in the instance segmentation, I mean, not only they tell you this is the bicycle, but also it is able to distinguish different bicycles for you. Okay, so it is obviously much more advanced than semantic segmentation. I mean, how they do this job? They are, actually using the mask RCNN. Okay, the mask RCNN is based on the faster RCNN. Okay, and I think I will skip this. Okay, if you are interested, you can check out the detail of this model. Actually, mask RCN is a very convenient model to use. Okay, along with several different projects. Okay, but because it is based on the faster RCNN. Okay, it is still kind of slow. Okay, it is still kind of slow. Okay, so anyway, the last slide. Let me finish this last slide. So TensorFlow offers a few other kinds of convolutional layer. The keras.layers.conv1D or conv3D. From the name you can tell. Okay, it is dealing with convolutional layer for one-dimensional or three-dimensional. We have talked about two-dimensional convolutional layer. So 1D or 3D, well, the idea is pretty much the same. Okay, in some application, we do need that. For example, conv1D, it can be applied for time series or text. Okay, because all these time series text, they are one-dimensional. Okay, and 3D. Okay. For example, like a 3D PET scan, okay, the positron electronic scanning. You'll get like 3D image for your body, okay, in hospital, okay. I did that like once, about 2 years ago, okay, because of my kidney stone, okay, and so if the input is something like 3D object, then the conv3D will be helpful. Okay, and there's also dilation rate. What is this dilation rate? Okay, it's like this. Okay, let me use the example. Okay, so for example, a 1/3 curve filter. Okay, if your filter is 1, 2, 3. Okay, after you apply the dilation rate of 4, okay, it is going to insert the hole between it's going to make your filter longer. Okay, it's going to make, you can see, each location, each member in the filter is going to be filled. Okay, in between it's filled by some zeros. Okay, and you could apply this filter, okay, just like the regular filter in the convolutional layer, and because there are a bunch of zeros, so when you do the computation for this type of filter, you have no computational price, no additional computational price, and no extra parameters that you need to worry about. Okay, so this is like a technique that we are going to use. Okay, later on. Okay, when we talk about WaveNet. Okay, and last one. Okay, the depthwise convolutional layer. Okay, so I think we talk about depthwise convolutional layer, right? So you apply this. To every individual input channel independently. So I think you get the idea. Okay, so we can use this to create like a depthwise convolutional layer. Okay, so I guess that's it. Okay, we don't have this because, for example, this one is actually not offered by the keras. Okay, but the keras 1D, keras 3D, conv1D, conv3D are both offered by the keras. Okay, just want you to be aware of that. Okay, so we are done with this chapter, and then now we are moving to the next chapter, which is sequential learning. Okay, so let's take 10 minutes break. When we come back, we will continue our discussion.